Hi, welcome back to an open introduction to basic logic. If you watched the previous videos in the series, we covered chapters 1, 2, and 3 of For All X, the Lorain County remix, which you can download. Just Google the title. I printed out a copy for my reference, but you could just follow along on the PDF. Now, throughout this video lecture series, I've suggested that you pause the video and complete exercises, either on the slides or from the textbook. In some cases, I'll be providing the answers to these problems in the video. In other places, you're on your own. So, if you're just jumping in now, that's fine. Chapters 1, 2, and 3 introduce some of the basic concepts in a formal logical system, but they did so in an informal manner. I talked a lot about different concepts like validity, tautologies, contradictions, consistency. We're going to be going over all of these again, but now in the context of a system of sentential logic. A formal system with a syntax, a semantics, well-defined rules, and means of testing for validity, entailments. So this is going to be actually really exciting. So if you're jumping in now, that's perfectly fine. If you're not, we're just going to be applying some of the stuff we talked about in the previous series in, finally, a more rigorous fashion. So thanks for being patient. Let's get started. Now, sentential logic is a formal system of logic, a language with a vocabulary, syntax, a semantics. Now, the vocabulary will comprise of all the elements that can be used in the language, and only those elements can be used. The syntax, what is the syntax? It's the rules used to combine these elements of the vocabulary to make grammatical statements in sentential logic. So the syntax tells you how to put together those vocabulary elements together to make sentences that are well formed, that are grammatical, that make sense. And finally, the semantics will tell us what these grammatical statements actually mean. So, there's some exercises. I've anticipated them here, so if you want to just refer back. Anyway, let's just get started here. What is the vocabulary of sentential logic of our formal system? Well, there's going to be three elements. First element, sentence letters. We're going to use uppercase letters, A, B, C through Z. And these are the variables that we're going to use to represent atomic statements, such as grass is green. Now, an atomic statement is a statement capable of being true or false exclusively. It's not an opinion, an argument, an interjection, an order. A statement is something about the world that can be said to be true or false. Even if it's an opinion, that's fine. If I say Radiohead is the greatest band ever, you can say that's not true. But if you're able to say, hey, that's not true, well, then you made a statement. So it's capable of being either true or false. The second element of our vocabulary, after the sentence letters, will be the sentential connectives. These will connect sentence letters to form complex statements. If you remember in the last video I said there are atomic sentences, complex statements. A complex statement is formed out of different parts. They are not, and, or, if then, if and only if. And these elements we're going to use together to combine, I dropped my marker, to combine the sentence letters. Finally, I'm back. We'll be using brackets and parentheses and typos, apparently, brackers. Is there the fifth typo I've noticed in these slides? We'll use them to disambiguate more complex statements of SL. And what I mean by that will be clear in a moment. So, sentence letters, connectives, parentheses. These are the three elements we are allowed to use in our formal system of sentential logic. Now, 4 of these 5 connectives are binary connectives because they always connect two other things, two atomic or complex sentences in SL. They are as follows: conjunction, and. We're going to be using the and symbol. An example here is P and Q. Disjunction, or, a little lowercase v there, P or Q. The conditional, an arrow representing if then. Example, if P, then Q. Finally, the biconditional, which is going to be more technical, but it'll play an important role in our logic. The if and only if. P, double arrow, Q. So a complex sentence of SL might be something like if P, then Q and R, or if P, then Q and R. And these are actually going to be different. Now, what I mean by binary here is actually pretty important because the connectives are always connecting two chunks of things at a time. And the reason we have brackets and parentheses to disambiguate is to make sure we know which chunks are being connected, because things are always going to decompose into two subcomponents. What I mean by that will be clear once we have some examples. So just remember the symbols, because we're going to be using them a lot. And, or, if and only if. Now there's one left, the negation. It's different. It doesn't connect two elements. It will always operate on one element. So if we had the negation at the bottom there, we see it means not. It's a little tilde symbol. And we're going to put it in front of something like not the case that P is true. So again, we have and, or, if and only if, not. The first four are binary. They connect things together. The last one is not binary. It operates on something. So let's talk about negation a little bit. Negation can be placed, because it's different, right? It can be placed in front of any atomic statement, any complex statement. Its role is to reverse the truth value of whatever the statement is by saying it's not the case that. Now the truth value, if you recall, is the value that the atomic sentence or complex statement has. Bivalence, as we saw in the last video, says things are always either true or false. That is called its truth value. Its truth value could be true or false. Why not the false value? I don't know. So the role of the negation is to flip that truth value. So if I say the sky is blue, I can represent that by S. If I say tilde S, I'm saying not S. I'm saying it is not the case that the sky is blue, which is false. So as a general rule, by the way, sentences in English, negative sentences in English, should be symbolized as a negated atomic sentence, with the sentence letter representing the concomitant positive statement. So if I say, I don't like puppies, your best practice would be to say tilde P or not P. It is not the case that, what? I like puppies. You might be tempted to translate sentences, negated English sentences, when we're doing translation as D, do not like puppies. Look, and you could. Technically, it's not wrong. But I find it's a lot easier to keep track of the meaning of my symbolizations if I always use sentence letters to represent positive statements. Consider the double negation. Not P. It is not the case that I like puppies. It's not the case that I don't like puppies. Versus not D. It's not the case that I do not like puppies. Right? Which one is easier to understand? So my advice to you is, as you translate, try to keep things positive. And then if you have a negated statement in English, use that not operator. It's going to be really useful. Now the textbook, if you're reading along in the chapter here, chapter 6, where we're talking about sentential logic, on page 177, 78, your pagination might be different. There's some cases where you might not want to do this, right? The authors, they give an example, something like, Elliot is unhappy does not mean the same thing as it is not the case that Elliot is happy. Now, is it possible to not be happy without being unhappy? I don't know. Honestly, all that stuff feels like a trick question. I don't believe in trick questions. So don't worry about it. If a statement looks like it's expressing a negative claim, just go ahead and assume it's expressing a negative claim and do what I suggested, which is use that tilde operator, use that not. Because I'm not going to try and, I don't think it's not good pedagogical practice to get cheap shots like that. Anyway, moving on. So I want to make all of this as clear as possible. So I'm going to introduce something called the truth table. The truth table is a way of summarizing how the sentential connectives operate on their elements. Now for a negation, for example, the truth table is pretty simple. Now, sentences are always either true or false. That's bivalence. And I'm going to represent that by having this A here. So A is, I don't know, apples are delicious. That's either true or false. So true or false in brackets here. And then tilde, the negation, means that it is not the case that apples are delicious. We'll reverse the truth value. So suppose apples are delicious is true. Then it is not the case that apples are delicious is going to be false. Right? Because the truth value, so if the truth value of A is T, then the truth value of not A will be F. So if A is T, the not will have value F. All right? Again, A can either be true or false. When A is true, in the case where A is true, not A will be false. In the case where A is false, not A will be true. So the idea is that the negation has an input. And the input of that negation will be the truth value of the sentence, the atomic statement, the variable. And that input is going to be in brackets on the right-hand side. And that input is then turned into an output, which is just the opposite value. So the truth table here is the negation takes a T, turns it into an F, or takes an F, turns it into a T. Now, if you're in a computer science course, you might be using ones and zeros instead of T's and F's. But actually, the truth tables and the whole notion of logic gates or connectors works exactly the same. You just substitute 1 for T and 0 for false. Otherwise, this inverter, the not, works exactly the same. But this is a philosophy course, so we're going to be sticking with true or false in arguments a little bit. Actually, not a little bit, entirely. So, now that we have the notion of a truth table in our back pocket, why don't we have truth tables for all our connectives so we understand how they work? Conjunction means and. It's a binary connective. That means it's going to take, unlike the negation, 2 inputs. Now, P and Q. Suppose P is, I like playing video games, and Q is, I like Quentin Tarantino movies. So P and Q says, I like video games and Tarantino movies. Now, this truth table here has 4 rows. Why? There are 4 possible inputs to the AND, which is true only when both inputs are true and false otherwise. So let's go row by row here. So the AND is a binary connective. It's connecting 2 elements, element P, element Q. P can either be true or false. Q can either be true or false. How many combinations are there? Well, they could both be true. One can be true, the other one false. One can be false, the other one true, or they can be both false. This exhausts all the possibilities given by valence. P is either true or false. Q is either true or false. How many combinations are there? There are 4 possible combinations. True, 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 false, false, true, false, false. So what the truth table here is doing is it's giving the value of the AND, of the state of the complex statement, P and Q, for every possible value of its components. So when is the AND true? It's true when both sides are true, when P is true and Q is true. Otherwise, think of it as a lie. When am I saying something that's not true? When am I lying? Suppose I like video games, but I don't really like Tarantino movies. I just said it because I want you to like me. So, yeah, I like video games and Tarantino movies. Yeah, what's your favorite? I haven't watched any. Then that statement would be false, because it would be P is true, I like video games, but Q is false. I don't, in fact, like Tarantino movies. I've never seen any. So true, false, and the middle value here is false. Right, because an AND statement is only true when both of the things connected by the AND are themselves true. That's the meaning of AND. Now, what's really interesting here is that I've defined a unit of meaning, AND, which has a sense in English, a semantics, using something really more primitive, a 2-value truth table, T and F. With the meaning of AND is just its truth table, the fact that it's true when the truth value of its components are both true and false otherwise. So this mysterious linguistic unit of meaning, the AND, has now a precise definition. P is true, Q is true, therefore P and Q is true, and it's going to be false otherwise. This leads us to actually a really nice example of a valid argument using only the truth table as a proof system. So let's look at that. Suppose I say P and Q, premise 1. Conclusion, therefore P. Now, the definition of validity is that if the premises are true, the conclusion is also going to be true. The truth of the premises guarantees the truth of the conclusion. It's impossible to have true premises and a false conclusion, in other words. So if the truth of the premises guarantees the truth of the conclusion, I should say the following. I'm going to test for validity here. So I'm going to assume the premise is true. I'm going to put a big old T here above the AND. Why? Because I'm checking to see if the truth of the premises guarantees the truth of the conclusion. So I'm going to say, yeah, this premise is true. What does that entail? Well, here's what it entails. Now remember the truth table for P and Q. It implies that P is true and Q is true, because there's no row on the truth table where, in other words, every other row makes this false. There's only one row where P and Q is true, where the value of P is T and Q is T. So conclusion, P must be true. Could it be false? Could I be misled? Could I have an invalid argument? No, because if this were false, then I would not be making a true statement. I'd be false, true, true? That's impossible. There's no row on the truth table that says that. The and specifies that the premise P and Q is only true when both of its components are true. So if I have an argument, I like video games and I like Quentin Tarantino movies, therefore I like video games, is a valid argument, because it's impossible to have true premises and a false conclusion. In other words, if the premise is true, the conclusion must be true. Right? Let's look at that again. If P and Q is true, what else do I know? I know that P is true and Q is true. So I have a valid argument if I infer P from P and Q. Now that seems like a trivial example, of course, but if you understand the basic reasoning we used here, which was that the truth of the premise implied a truth value of one of its subcomponents, then we've basically understood what we need to understand about testing validity and logic. Everything else is just slightly more complicated variations on this theme. So why don't we look at some other truth tables? Why don't we look at other truth tables? I have another slide. Okay, let's talk about something before we move on to the next truth table. This is live. I'll cut it in post. Now, of course, many of the features of natural language are lost in SL. I just waxed poetic on how we managed to define this mysterious linguistic entity and solely in terms of bivalence in a truth table. Well, that's sort of true, sort of not true. Because many of the nuances and shades of meaning in natural language are completely lost in a formal system. For example, I can say, I love Lord of the Rings, but I didn't like the Hobbit movies. Although I loved Lord of the Rings, I did not like the Hobbit movies. I love Lord of the Rings, and I did not like the Hobbit movies. How would I translate these? They're all the same. L and not the case at H. Right? Like, I love Lord of the Rings, and it is not the case that I loved Hobbit. Right? L and not H. Words like but imply, they set up an expectation, a contrast. Right? If I say, I love Lord of the Rings, but I didn't like the Hobbit, right? I'm implying that there's kind of a relationship between these two statements. Like, you might have expected me to like the Hobbit because I love Lord of the Rings, Peter Jackson, Middle-earth, Tolkien, all those things, but I didn't. Logic loses all that stuff. So the slightly different shades of meaning in those three sentences are all going to be reduced to the same thing, L and not H. Again, if we go back a video, I talked a lot about the expressive power of different logical formalisms. Right? Aristotle's logic does some things, but it doesn't do other things. Likewise, natural language, like English, has all kinds of features, like contrastive expectations. Is logic going to capture but? No, it's not. So if you see the word but, you're going to want to just use the and, because there's no but operator. That's a completely different thing. But operator. I'm going to edit that one in post too. So if you see two sentences and the implication is that they're both they're going to be joined in a certain way, then just use that and operator, because there's no although operator. There's no but. Okay, so that's what I want to say about conjunction there. Now I'm ready to move on to the next truth table, which is for the disjunction, the or. The first thing you want to notice about the disjunction here is that, again, we are joining two components. In this case, for this example, we're going to be joining just two atomic sentences, P or Q. But later on, we're going to see that it's quite possible to join like more complex sentences together as long as we keep up this binary separation. But that's for later. Now, the first thing to notice about this truth table is that it's only false in one case, when both of its inputs are false and it's true otherwise. This is known as inclusive or. It's still true when both conditions are satisfied. So it's not the soup or salad restaurant or. It's more like the, I'll play GTA or Overwatch and then you end up doing both. I didn't say something false. Right? When is it really falsified? Think about the falsification conditions. If I say, I'll clean my room, or I'll do the dishes, I'll do something. When is that false? When would somebody say, hey, you lied, when I didn't do either of those things? But if I say to my wife, yeah, I'll do laundry and the dishes, and I end up doing both, I'll do laundry or the dishes, and I end up doing both, she's not going to say, you liar. She's going to be like, huh, good for you. Right? It would only be a lie if I do neither of these things. So let's look at this truth table here. P or Q. True, true, true. True, false, true. False, true, true. False, false, false. So exclusive OR is its own thing. The super salad OR, like you can have one or the other but not both, that's its own thing. And we can represent that in sentential logic. We just don't have an operator for it. And we're going to get to that shortly, how to represent more complicated statements. But for now, let's just learn the operators. So there's one condition where the disjunction is false when both sides are false. Okay, and I just want to point out one very important thing here. You're going to want to memorize these. The truth tables, don't refer to them. Don't flip pages back and forth. Don't come back to the video. Memorize them. Be able to just write them down without thinking reflexively. You should know the conjunction is only true in one case, when both of its conjuncts are true. You should know that its junction is only false in one case, when both of its disjuncts are false. So you should be able to just write out the truth tables at the drop of a hat, memorize them, memorize them, memorize them. Okay. So inclusive and exclusive OR. The disjunction, the OR as we defined it as a logical operator that we have, the little lowercase v, is always going to be inclusive OR. Now, super salad implies you can't have both. So, because most logic professors don't believe in trick questions, and none of my assignments or anything will have trick questions, just assume that we're always going to be doing inclusive OR, and that exclusive OR will always be clearly marked as such. So if we're going to be having an exclusive OR for whatever reason, I'm going to tell you. Generally speaking, always assume that we're going to be dealing with the regular inclusive OR. Another thing to notice is that if we use negation in conjunction with disjunction, we actually get some interesting things. So let's look at our first dual operator sentences here. All right, why? Because it's atomic sentences plus not just one operator, but two operators. So let's look at the difference here. Not P or not Q. Right, I'm saying either what? Either what? Either not P or not Q. Why? Because the OR is joining two things. It's joining not P on one side and not Q on the other. Let's look at the second one here. Here the negation comes first. So I don't start the sentence either not P or not Q. I say it is not the case that either P or Q. So what's different? The negations are operating on the atomic sentences directly in one. The negation is not either not P or not Q. But in two, there's only one negation, and it's operating on the disjunction. It is not the case that either P or Q. And if, keep those in mind, we're going to, these kinds of things are going to be really important, because more complex truth tables, when you have more than one operator, are going to be crucial to having a formal logical system with sufficient expressive power to be interesting. So, let's notice something here. So, not the case that either P or Q. What I'm saying here is it is not the case that either P or Q is true. So when would I expect that to be true? When P is false and Q is false. Let me give you an example here, right? Neither, if I say it is not the case that either P or Q, I could say it's not the case that I like Hawaiian pizza, and it's not the case that I like anchovies on pizza. So when is that true? When I don't like, this is a bad example, when I like Hawaiian pizza is false and I like anchovy pizza is false. So false, 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 therefore true. And this goes back to the disjunction table. Right? Notice this just is over here. This column here is a regular disjunction truth table. True, 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 false, true, false, true, true, false, false, false. That is the definition of my inclusive OR. And then what does a negation do? It takes this value here and just flips it. So the input for my operator here, and this is actually the main logical operator, which is something we're going to define shortly. The input is the OR, and the input of the OR is the P and Q. So we're going to work from all the possibilities of P and Q, True, true, false, false, true, false, true, false. In other words, all the combinations, true, false, true, 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 false, false, true, false, false. Those values are going to give you the values of the OR, and then the OR's values are going to be flipped by the negation. So true becomes false, and false becomes true. And that's how the truth table for a more complex statement is going to look like. Now again, rewind, pause, stop, write it out, look at the truth tables. But the important thing about the sentential connectives is that their values are always going to be determined by the values of their respective inputs. And there's always going to be an order of operations. So in both cases here, not the case of P or Q and not the case of P and Q, the negation is taking as value the input of the other operator here. So the negation is taking the input of the disjunction. The negation is taking the input of the conjunction. And so the regular, look at this is the same and truth table. True, false, false, false. The only thing that's happening is that this and is feeding its input to the negation, and the negation is just flipping it. True becomes false, false becomes true, false becomes true, false becomes true. That means also these statements are saying different things, right? It is not the case that either P or Q. It's not the case that either I like Hawaiian or I like anchovies. It's different from I don't like both things. I don't both like video games and Quentin Tarantino movies. One of these things is something I don't like, in other words. But the important thing for our purposes, of course, is to understand that when you're putting together the elements of our vocabulary, which is sentence letters, operators, brackets, is that the values here are a function of its input elsewhere. So the and, right, true becomes false because what the negation does just is to flip the value here. Now the brackets are also playing a role. If you look back a slide over here, what are the brackets doing? I said they would disambiguate. If I didn't have a bracket here, suppose I deleted it, right, the negation would be operating directly on the P, either not P or Q. But if I put in a bracket like this, now I'm saying something different. I'm saying it is not the case that what? Either P or Q. So the brackets tell me what the negation here is operating on. More examples will make this clear. So, one less, the conditional. Okay, so we're actually going to do the exercises here just to kind of understand a little bit how complex sentences are going to work when we have many different sentential connectives. And I'm going to define the actual syntax of SL a bit later. Right now, I just want us to get a little bit comfortable, start to know the symbols, understand how they work together. So let's start with you can have soup or salad, but you cannot have both. All right, so you can have soup or salad, but you cannot have both. So we're going to let S be soup. And, oh, S is already taken, so what are we going to do for salad? How about L for salad? We're going to represent it that way. So the sentence is, you can either have soup or salad, but you can't have both. In other words, it's the exclusive or. So let's pause the video. Try to figure it out. Did you pause? Okay, I'll give you the answer now. So you can either have soup or salad, but you can't have both. So why don't I just write it in English? So soup or salad, but not both. So let's identify the logical elements in the sentence as well as the possible atomic sentences, the variables. So we have soup, which we represented with an S. We have salad, which we represented with an L. We have an or. That's good. So we know that this part is going to be translated with an or. So soup or salad. But not both. We've already talked about the but. Roughly, it's going to be an and. Right? So again, in English and natural language, we're setting up a kind of a contrastive expectation. We're setting up like, oh, but you can't have But it really means the same thing from a logical point of view because of our restricted semantics. It really means the same thing as and. Super salad and not both. So we're just going to put this and here. Next, not the case. You can't have both. Not both. So we have a not, and then both. Both what? Both soup and salad, right? That's what that means. Not both what? Not both soup and salad. So it's implicit that we have an S and L. Not both soup and salad. But we're not done, actually. So this is a good start. But one of the things I maybe didn't do a very good job when I introduced these connectives is to really emphasize how the brackets are going to be used to disambiguate the logic so that the binary connectives, i.e. the connectives that are only connecting two chunks, two things at the same time, can really be clear. So we're going to try and use brackets to make sure that we have a disambiguated sentence such that our binary connectives are really only connecting two things at a time. Not necessarily just two atomic sentences either, but any two chunks, any two more complex things. So soup or salad, but not both. Where am I going to want to put those parentheses? Let's just run through it, right? So soup or salad. So we're going to want to say soup or salad and. Right, that's kind of the saying I'm saying. Here's what's happening, but soup or salad and not the case that both. Where am I going to want to put my other brackets? I'm actually going to want to put them here, after the negation, right? In order that we understand that it is not the case that both S and L. So this is how we're going to do exclusive or. It turns out we just need a slightly more complicated logical phrase. So here we have either soup or salad, and further condition, it is not the case that you can have soup and salad. So let's look at how this is connected in a binary format. We have the and here, which is connecting this sentence and that sentence. The or is the main logical operator here, and the not is the main logical operator here. So the value of this and is going to be a function of the value of the two things it's connecting. Suppose I want both soup and salad, say. So I say, I want soup and salad. I want soup is true, salad is true. So true, true, true. I want soup, I want salad. So I'm just kind of filling in true and false here at the most basic level, which is the atomic sentences. So true, true, true. Why? Because the and is true whenever both sides are true. And here my or is true because both sides, it's an inclusive or, true, true, true. You go back to the truth table. Now, what is going to be the value here? Because the value of the and is going to be the value of the negation. So true becomes false. So now I have true, false on an and. But and is only true when both of its inputs are true. So true, false, false. So I say, but I want soup and salad. And you can't. False. Soup or salad, but not both. So suppose I ask for both. The output is false. This is a pretty complicated example, given that we've just started. However, it's really important that we disambiguate the sentence so that only two chunks are being connected at once, and then we put a parenthesis in the right place so that we understand what the negation is operating on. Let me give you one more example, then I'll end the video, and then we're going to pick up on the next video to do the conditional. Okay. Now, one nice way to understand the importance of brackets or parentheses in terms of the binary nature of the connectives is that if I consider the difference between something like P and Q or R versus P and either Q or R. There we go. Actually, I'm going to have all three examples, P and Q or R. Now, this is sentence 1, this is sentence 2, this is sentence 3. Sentence 3 here actually is not a syntactical sentence of sentential logic. The reason is that we've defined that I said that, look, the sentential connectives are always binary. They always have to connect two things at once. But here, it's unclear how these chunks are supposed to work. So it's not grammatical. It's not well-formed syntax. It's unclear which of these two this sentence actually is. It has to be either, right, this or is connecting this chunk like this, right? Maybe, or alternatively, right, the and is connecting the two chunks. But if I don't have brackets, I can't tell which one is which. Because, again, all these connectives are supposed to be binary, except the negation. So that last sentence is not syntactical. And it makes sense if you think about it, because these two are actually saying different things. P and Q, or R, so is actually really different from P is true, and either Q or R is true. So if you fill in P, Q, and R, these sentence letters with some example, suppose video games, Quentin Tarantino movies, and Reddit. So I say, so I say, hey, what does he like? Well, he likes either video games and Tarantino movies, or he likes Reddit. Weird example. And there's a different interpretation. He likes video games, and he either likes Quentin Tarantino or Reddit movies. He either likes Quentin Tarantino movies or he likes Reddit. So the meaning of the sentence is actually quite different. Saying either of these two things is true, P and Q or R. That's different from saying P is true and either Q or R is true. The main logical operator, now the notion of the main logical operator is the one that connects is kind of the thing that connects the overall sentence into two bits. So this is, right, part one, this is part two of the sentence. The role of the main logical operator is to divide any sentence in SL into two parts. Because the sentences are always, right, the sentential connectives are always binary operators. So the main logical operator is the one that tells you, here's chunk one, here's chunk two. The main logical operator here is the or. What's the main logical operator in sentence two? It's the and. Why? Here's chunk number one, here's chunk number two. Every well-formed syntactical, grammatical sentence of sentential logic is necessarily going to be divided up into two parts through the main logical operator. And then, after that, it might be divided into further subparts, right? So the secondary logical operator here is the or. And it's going to divide into these subparts, right? So it's always going to carve out that way. Negation, of course, is the only exception to the binary rule, but that's actually pretty easy to figure out. So next slide, next video, where I'm going to introduce the conditional truth table, which is slightly more different, slightly more complicated than the conjunction and disjunction. And after that, we're going to be working on more complex sentences, and hopefully I'll be giving you an actual formal definition of the syntax of SL. Hope this has been useful.